Okay, we're gonna get started. Rich Ozer here and Gerald McKeegan. Gerald, your video's off. You need to turn on your video so you could wave to everybody. Find it? Prompt you there. Get started. All right, there we go. Great, we're all online. So we have a clear night tonight. The only thing we're competing with is probably the loudest fireworks show I've ever heard in Oakland in 30 plus years. And it's not an official show, of course. It's evenly distributed across all of our neighborhoods. So I hope everybody is being safe and having a good time tonight, keeping your pets indoors. It's quite an amazing sound from up here because it echoes all the way up the canyon to the Science Center. In any case, we've got clear skies tonight, so we might actually be able to show you something. Gerald, we're going to start by talking about tonight's moon, right?
Yeah.
All right, let me share a slide here. And
let me get off mute here.
All right. Hold on for a moment. I'll share this slide and then you can start talking about it.
Okay. Yeah, so tonight is a full moon. If you look outside to the southeast, you'll see that the moon is up. And tonight is also an eclipse, but it's a special kind of eclipse called a penumbral eclipse. The Earth's shadow, as you can see in this diagram, actually consists of two parts. The inner circle is the dark shadow of the Earth. So the sun is shining on the Earth, and behind the Earth, it is casting a shadow out into space. And the part of that shadow that is fully dark, where no sunlight reaches at all, that's the very dark part. When you see a total lunar eclipse, that part actually looks a little rusty red because of refraction through our atmosphere. The outer circle is what we call the penumbra. And it's a region where there's a little bit of light depending on what angle you're at. So it's not a completely dark shadow. And right now, the moon is passing through the penumbra. Now, the diagram that Richard has put up here shows the moon passing fully through the penumbra. Actually, tonight, it's only passing partly through the penumbra. So it's only the northern third or so of the moon that's passing into the penumbra. The penumbra is not a very dark shadow, so it's really hard to see the difference. In fact, we were outside a few minutes ago looking at the moon, and we can't tell that there's a shadow on it at all. But it is happening, and if you want to go outside and look at the moon with a pair of binoculars or something, you might be able to detect a slight shading of the northern third of the moon. And that's going to continue. It will fully exit the penumbra at about 10:52 tonight. And it started earlier tonight at around 8:07 when the moon was still below the horizon. The moon didn't rise above our horizon here in the Bay Area until about 8:30. So the eclipse was already in progress when the moon rose. So you might want to take a look, but don't be surprised if you don't notice any difference between the northern part and the southern part of the moon. It's a pretty faint shadow on the moon. All right. So you got to unmute. There you go. You're still muted.
All right, I'm not muted anymore.
There you go.
Everybody's probably better off with me muted anyway, so that's all right. All right, so next on the agenda.
Well, it's a clear night, and we've got low humidity, so I think that means we have observing conditions. So why don't we go ahead and open the roof over Nellie? We see Nellie behind you there. What I'm going to do now is open the roof. So prepare for a little bit of noise as we open it up. Gonna hear some buzzing sound here. Maybe. There we go.
You had me worried there for a second.
Yeah, had me worried. Seems like this whole year has been one bit of bad luck after another. So you see that the roof has a little notch in it. That clears the telescope. And once it's all the way back, we can go ahead and start raising the telescope. Takes a little bit for the roof to come all the way open. If we don't open it all the way, it won't get to its catches. It's got some shoes at the end of the travel.
There now.
Yeah, it's got some shoes at the end of the travel, and we have to get there's some cleats that go into those shoes, and that's what keeps the roof from blowing away. So if we get a lot of wind up here, it could actually pick up the roof and blow it away. So there's some cleats back there that hold onto the roof and keep it from blowing away.
Somebody mentioned that it sounds like it needs some WD-40.
Yeah.
And well, everything needs WD-40.
Right. I'm not sure how much of what you heard was the roof and how much was all the fireworks going
Yeah,
on
right.
there.
Well, if we use WD-40, we would be buying it by the barrel.
Okay, well, Richard, you've got your camera already
Yeah.
on the telescope.
Let me go ahead and do a screen share.
And
There we go.
I thought one of the interesting, that's the focus image that you had earlier.
Yes.
So one of the things
that was just a double star that we put it on earlier.
right. So one of the things I thought would be interesting to do. The Milky Way is starting to rise on the eastern side of the sky. But if we look to the west, we're looking away from the Milky Way. And there's quite a difference in the amount of stars that we can see. Hey, can you mute for a second? Because I'm getting an echo.
Oh, sure. Sorry about that.
Sorry. Yeah. Okay. All right. So anyway, the Milky Way is rising in the eastern sky. And if we look away from the Milky Way, we're basically looking out into deep space. And there's quite a difference in the number of stars that we would see in the field of view looking away from the Milky Way versus looking toward the Milky Way. So I thought it would be cool if we just kind of point the telescope to a spot off to the west a little bit and go ahead and just shoot an image, maybe a 30-second exposure, and see how many stars we see when we're looking away from the Milky Way. And then we'll turn the telescope and we'll point it into the Milky Way, and we'll see how many stars we see when we're looking in the Milky Way. So I'm gonna go ahead and slew the telescope. And we're just gonna slew a little bit to the west here. Okay, yep. So Richard's going to go ahead and shoot a 30-second exposure with his camera, and we'll see what it looks like. Should see a few stars. He's getting it set up here. There we go. So if you look at the image, I think he's going to stretch it a little bit now here. Yeah. But even with this image, you can see there's very few stars in the image here. And when he stretches it, you can see the little donuts you see there, the dark donuts. Those are specks of dust, either on the camera chip itself, or possibly on the secondary mirror or on the primary mirror. Most likely it's on the camera chip itself because they're so small. But the stars, there aren't very many stars in that field of view. Yeah. So what I'd like to do now, I'm going to slew the telescope pretty far over to the east. And I want to make sure I can go that far. Yes, I can. Okay. So we're going to go ahead and slew way over to the east and then shoot again into the Milky Way. And you'll see the difference in the number of stars. So away the telescope goes. One of the nice things about this telescope is it's all computer controlled. So all we got to do is go to the computer, tell it where we want to look, and it does all the work for us. We have two other observatory telescopes up here, Rachel and Leia, and they are manual telescopes. When we want to move them, we have to unlock the telescope and move it by hand, which is a lot more work. Okay, so we're now pointing into the Milky Way galaxy, and Richard's going to do another exposure under identical conditions, and we'll see how many more stars we see in the field of view. You're doing what, a 30-second exposure? Yeah. So you have to give us a little time for us to do the image. And whoa.
That was a good experiment.
Yeah.
That worked.
Yeah. Now, if we did an even longer exposure, or if you stretched it, I'll bet you'd see even more stars in the field of view.
Well, that's pretty cool. That was completely unrehearsed. And if we had shown the same amount of stars under both circumstances, then we would have been liars, right? So anyway, that's actually one of the big challenges when doing photographs along the plane of the Milky Way, is sometimes there's so many stars that it obscures what it is you're trying to shoot, and you have to do special processing techniques to reduce the size of the stars, or sometimes eliminate the stars altogether because they get in the way of what you're trying to show in the photograph. But yeah, this was a good experiment.
Yeah.
You can also see what happens when you have a bright star in the field of view on a photograph. You see how it's kind of bloomed and bloated, and that's a big problem when taking astrophotos as well. Whenever you have a bright star in the field of view, it requires special treatment, and otherwise it overwhelms the image.
Yeah, I was just picking a random location in the Milky Way, so sorry about the extra star there. So, but yeah, one of the things we did with Nellie, we actually do a little science with it. We use it to track near-Earth asteroids. And asteroids often look like faint stars moving against the background of stars. And when you're shooting into the Milky Way, it can be very hard to find the asteroid because there are so many stars in the image that it just kind of wipes out the asteroid. It can be pretty tough to do. Okay, well, so we did that demonstration. So now you got an idea of what it looks like when we look into the Milky Way. If you're standing outside, of course, in the Bay Area, you can't see the Milky Way. But if you're off in the woods somewhere, high in the mountains, this time of the year, and you look into the sky, especially around midnight, you'll see the Milky Way arcing across the sky. And it looks more like just a bright fog or cloud that arcs across the sky. But what you're actually seeing is billions of stars. You're looking into the disk of the galaxy where there are billions of stars. Most of them are so far away that with our naked eye, we can't really make them out as individual stars. But we see the combined glow of all those billions of stars. And that's what gives the Milky Way its milky appearance. Okay, let's see. We had a couple of objects that we wanted to show you, some deep sky objects, one of which was the Ring Nebula. also known as M57 or Messier 57. So what I'm going to do now is slew the telescope, and we may have to do this in a couple steps to make sure that the telescope is properly aligned with the sky. So bear with me here for a second. Richard, if you want to chat while I move the telescope.
All right, there we are. I got the right computer. You know, we have 3 computers going, and it's really easy to get the audio going on the wrong one. So yeah, what we sometimes have to do with this telescope is find a bright star in the part of the sky we want to be looking at, and find that bright star in the field of view of the camera, sync the telescope to the star, and then travel to the very dim object that we're looking for. It's kind of a standard technique to get the telescope synchronized with the part of the sky that we're looking at. And it almost doesn't matter, you know, what telescope we're working with. It's kind of a standard technique that all astronomers use to align the instrument. But
why don't you go ahead and shoot maybe a 10-second exposure?
all right, we'll do 10 seconds, you say? Okay.
Yeah. Too much.
Yeah, we'll see. That's not too bad. Do we want to get it centered?
Yeah, hang on
Okay,
just a
hold on.
second here.
Let me put it on live view, and then we'll. There we go. The other way. There we go. Okay, perfect.
All right. And I'll sync it. And then let's go to M57.
Okay.
Yeah. So we're doing a 30-second exposure of M57, the Ring Nebula. The Ring Nebula is what we call a planetary nebula. It's gas shed by a dying star. So this star was once probably very similar to our sun, but it got very old. As it got old, it swelled up and became a red giant star. As a red giant, it began losing its, there it is. All right.
Well, that's much better than I expected.
Yeah, that's
So that's excellent. The star that created this this ring of gas has evolved into a white dwarf star, and you can see it in the center of the ring. And if I point it out, in fact, right, find my mouse now, right there. You always know where it is by looking for the arrow. There it is. So you could see the white dwarf star in the center of the planetary nebula. And all planetary nebula will have something like that. Whether you could see it or not depends on whether or not you're looking into the poles of the planetary nebula, or if you're looking at it from the side. And in this case, the pole opens up right towards us.
Yeah, so I was explaining a little bit about what planetary nebula are. The star, as it gets old, it becomes a red giant. And as a red giant, it is very large. Can be more than 100 times its original size. So imagine this is what's going to happen to our sun here in about 6 billion years. Imagine the sun being more than 100 times its current size. When the star is that big, its gravitational hold on its outer layers is pretty weak. At the same time, there's a lot going on within the star. There's a lot of turbulence and convection going on, which produces strong winds. And those winds can literally blow the outer layers of gas off the star out into space. And see Richard's playing around with stretching the image here a little bit. So the star begins to lose its mass over 100,000 years or so. It blows gas out into space, losing its outer layers, eventually exposing the inner layers of the star, which are much hotter. And at some point, the star also runs out of fuel at its core. When it runs out of fuel, the fusion process, which has been producing all the heat of the star and which produces the internal pressure, which keeps the star expanded, that fusion process stops, and what's left of the star collapses into what's called a white dwarf. Now, this is a star that maybe was 1 million miles across when it was nice and young and in its vigorous years. As a white dwarf, it has shrunk down to be maybe 8,000 or 10,000 miles across. So it's much smaller, but it still has all of the heat that it had just before it collapsed. And that heat is now condensed into a very small space. So the star becomes extremely hot. And the star is also composed of a different kind of matter than ordinary matter. It's what we call degenerate matter. And with degenerate matter, it has to do with the structure of atoms and the electrons and their ability to absorb energy. As a result, the star is emitting a lot of heat, but there's no fusion or anything like that going on. It's just emitting all that residual heat that was left over from before it collapsed. And that heat, because it's so intense, comes off to a great extent as ultraviolet radiation. And the white dwarf is surrounded by all the gas that it was expelling before it collapsed. And the ultraviolet radiation goes out and it hits that gas, ionizes it, and causes it to glow. And the colors of the gas that we see is dependent on the composition of the gas. So if you look at Richard's image here, you see at the very outer edge, it's red in color. And that means that there's a lot of hydrogen there. In fact, the cloud is mostly hydrogen throughout. But at that very edge, there's a lot more hydrogen. Hydrogen, when it's ionized, glows in a deep red color. We call it hydrogen alpha. And so that red color that you see tells us that there's hydrogen there. But there's also in this cloud a small amount of oxygen. And oxygen, when it's ionized, glows in kind of a bluish green color. So you see a lot of blue-green in the cloud. Now, based on the coloring, you would think, okay, that means there's a lot more oxygen than there is hydrogen. But that's actually not the case. The oxygen is quite a bit less than the hydrogen, but oxygen, when it's ionized like this, it glows really bright in that blue-green color, whereas the hydrogen glows a very dull red color. So the oxygen, even though it's the quantity-wise, there's less of it there, brightness-wise, it overwhelms the red color of the hydrogen.
I'd also like to point out one other factor. We're using a DSLR camera, which is this is a standard off-the-shelf Canon camera that you can get at Costco, right? So the camera itself is much more sensitive to green and blue than it is, or green in particular, than it is to red. For every red pixel, there are 2 green pixels. And so as a result, it is biased towards the oxygen part of the spectrum. And to make matters worse, these cameras have an infrared filter over the sensor that blocks out probably, I don't know, 30% or so of the red color that you would normally get from an object like this. And there are actually places you can send your camera to have surgery done on it to remove that red filter for astrophotography purposes. But that's aside from the fact that the oxygen does glow much more brightly than the hydrogen when it's ionized, the camera is also biased towards the part of the spectrum that the oxygen glows in.
Okay, so this is a planetary nebula. This is the Ring Nebula, but the class of nebula that you see is called a planetary nebula, and there are actually a lot of them out there. There are many stars that go through this process. The cloud that's shed by the star can be very symmetrical. This one looks like a ring. We're pretty sure, though, that what you're actually looking at is down the tube of a cloud of gas that looks more like an hourglass. So it's very common when these stars shed this gas, it comes off the poles in sort of an hourglass pattern. So if we could somehow take that cloud and turn it 90 degrees, it would have an hourglass shape to it. It just happens to be oriented so we're looking right down the tube, giving it that ring appearance.
Maybe we should put it on M27 to illustrate that.
Yeah, okay.
Yeah,
Richard,
since we're on the topic, we might as well look at one that, from the side, right?
Right.
You can see exactly what we're talking about.
Right. So why don't we go ahead and go to M27. I'm going to take us to Albireo first, so we can resync the telescope, but also get a chance to see two stars. Yeah. So let me go ahead and start the slew here.
Albireo is the favorite double star for UC Berkeley.
And you'll see why in a minute. Hopefully the colors will show. All right, go ahead and take the picture.
Yep, dead center.
All right. Geez.
All right, that was good. Well, you can see why it might be the favorite double star for Berkeley. I guess it's the Berkeley colors. This is a really neat double star system because it's one of the brighter double stars that we like to show, and the contrast in color is so obvious and profound. It really demonstrates how different temperatures of stars emanate different colors. And for a long time, no one was really certain this was even a gravitationally bound double. And there was a satellite that was, it was an astronomical observatory that was launched many years back called Hipparcos, which gathered very carefully the data on the orbital elements of these two stars, and finally determined after many years of study that these two stars are actually gravitationally bound. But they don't orbit each other very quickly. It's like a 1,000-year orbital period or something like that.
Yeah, they're actually about 3 or 4 light years apart. So it's a very slow orbit. And you notice the colors. One is yellow and one is blue. And the colors tell astronomers the temperature of stars. Now, we just say yellow or blue, but an astronomer would look at the star with some instruments that would actually measure the brightness of the star across the whole spectrum. So you imagine all the colors of the rainbow. They would look at how bright the star is in every single color of the rainbow. And what they would see is that the yellow star is brighter in the yellow part of the spectrum, and the blue star is brighter in the blue part of the spectrum. And by very carefully measuring the exact wavelength that the star is brightest at, they can actually calculate the temperature of the star. And it's actually a relatively easy calculation to do. Once you've precisely measured the brightest wavelength, you just plug it into the formula and you get a temperature for the star. Now, most people, they go by what they see in their bathroom, the hot water faucet is red and the cold water faucet is blue. And that just confuses the heck out of astronomers, because in reality, under the rules of physics, it's exactly the opposite. Hot is blue and red is cool. And what you can do is imagine if I took a piece of iron and stuck it in a forge and let it heat up a little bit, it would be red hot. If I put it in even longer, it would be white hot. So the white color is clearly hotter than the red color. If we really heated it up, it actually would have a bluish white tinge to it. So blue is hot and red or yellow is cool in temperature. Now the other thing is you look at these two and one's obviously brighter than the other. And that can fool you into thinking that the brighter one must be the closer one, because they are separated by quite a bit. But you'd be wrong. Turns out the brighter one is farther away. The reason it looks brighter is because that's a star that is starting to move into that red giant phase that we were talking about. So the star has swelled up. It used to be a hotter surface temperature, but as it swelled up, became a red giant, the outer surface cooled, and it now shows that yellowish orange color. So because it's much larger, it has more surface area to radiate light. So even though the surface is cooler than the blue star, because it has so much more surface area, it makes the star appear brighter to us. And that star is actually farther away than the blue star, which is still in the prime of its life, hasn't yet reached the point where it's turning into a red giant.
We had a few questions. One of them is, if this was the UC Berkeley double star, is there a Stanford double star? Great question. I would have to say yes, and I would say that would be Eta Cassiopeia, which is a red star next to a white star. We can't show you that tonight. Later in the year, when Cassiopeia is higher in the sky, that's actually a very interesting star to talk about.
Yeah. Maybe we can figure out a night when we could get both of them on the same night, and then we can argue about who gets the axe.
Yeah, that's right. And Gerald answered the other question about which one is farther and closer. Then we got a question from Dan. Will they resolve with an 8-inch telescope? Absolutely.
Oh, yeah.
You can see Albireo naked eye. You can't split them with your eye unless you have like really phenomenal eyesight. But you can certainly see a single pinpoint of light where it is, so it's easy to find. And a pair of binoculars is all you need in order to split the two. All right.
Okay, so should we? All right.
This is our previous picture. We're going to be slewing in a second to M27, which is another planetary nebula, otherwise known as the Dumbbell Nebula, not because people who look at it are dumbbells, but because it's shaped like a dumbbell. And it is a good example of looking at a planetary nebula more from the side. So you can see the hourglass shape that is created when these hot white dwarf stars have outgassed their material.
You can go ahead and shoot now, Richard. Yeah, so when we were looking at the ring, like I said, we were looking sort of down the tube of what looks like an hourglass. With the Dumbbell Nebula, you get a lot of material coming off the poles, but it doesn't really look like an hourglass. It's more of a kind of a butterfly shape. And you'll see that here in a minute when Richard does his imaging. This object's a little bit fainter than the Ring Nebula, so it might not show up as well. Maybe need to do a longer exposure, but we'll see how it works out. Oh, yeah.
Yeah, you could see we need a longer exposure.
Yeah, we,
But, we'll try.
well, while Richard's fiddling around with that, trying to get as much out of it as you can, you can see that there is a white dwarf kind of at the center of the two dumbbells. And then you can see gas has come off on either side. That's gas that has come off mostly off the poles of the star as it grew very large, became a red giant. The star has now collapsed, become a white dwarf, and left behind again this gas that is glowing because of the ultraviolet radiation being put out by the white dwarf. And once again, you see the bluish green color of the ionized oxygen, and it's kind of hard to pick out, but if you look at a little farther away from the star, you can see two arcs on either side that are reddish in color, and that's the hydrogen.
I'm taking another shot here.
Okay. Okay, Richard's doing another image with the higher ISO setting, which makes the camera more sensitive. And hopefully we'll get a little bit more out of that. All right, there's the new one. Looks like it's a little bit brighter. Yeah, there you go.
That'll have to do.
Yeah, yeah. So again, the bluish green color, he's messing with the color histogram a little bit here, but the bluish green color is the ionized oxygen, and then the red fringes that you see there, that tells you that you've got hydrogen there, which is what we expect. Most of the gas blown off by the star is hydrogen. All right. Just got reminded by my virus protection that there were no viruses detected. Do we want to try M13 now? All right. So what we're going to do now is go to M13, called the Hercules cluster. It's a type of star cluster called a globular star cluster. And we're going to do a 2-hop jump here so we can make sure that the telescope is synchronized. So I'm going to go first to a star. And we'll do like maybe a 5 or a 10-second image just to make sure we're synchronized.
I'll just put it on live view. Okay. There's our star.
All right, and you're on live view?
Yep, I'm on live view.
Okay. All right. Got that centered up. And now let's go to M13, which will probably show up in live view as well.
I'm gonna wait and do a real exposure.
Okay.
Let me know when you're there.
Okay, we're there.
Okay. I'm gonna shoot 20 seconds at 1600.
Okay. So while he's doing that, let me tell you what we're looking at. It's called M13. A globular star cluster is typically a group of stars that formed very early when the galaxy was first forming. And they formed out near the fringe of the gas cloud that condensed to form the galaxy. Sometimes they're also caused by the galaxy absorbing dwarf galaxies. This one is about 23 to 25,000 light years away. And it has about 500,000 stars in it. And the stars in the galaxy or in the cluster orbit around the center of the cluster in highly elliptical orbits. So imagine an oval shape that's highly stretched out. That's the typical orbit of the stars around the center of the cluster. They go in, they get very close to the center of the cluster, and then they swing out and they go way out to the periphery of the cluster, and then they swing back in. When they're close to the center of the cluster, they're moving very rapidly in their orbit. And when they get out towards the outer part of the orbit, they slow way down and move very slowly. And because of that, the stars actually spend most of their time away from the center of the cluster. But you notice it's very dense near the center of the cluster. There's some debate about whether or not there is an intermediate mass black hole at the center of the cluster. So we're kind of still not 100% sure. There's another globular cluster that we'll see a little later on in the year. We do know it has an intermediate black hole. We're still not sure about M13. M13 is a very popular globular cluster for amateur astronomers because it's nice and big and bright, and it's very easy to find. There is a pattern of stars in the constellation Hercules that we call the Keystone. When we see a pattern of stars within a constellation that looks like a familiar object, that's called an asterism. And the asterism called the Keystone actually looks, it's 4 stars that are in the pattern of the keystone that you might see at the top of a stone arch. M13 is on the side of the keystone, more or less halfway between 2 of the stars. It's a little closer to one than the other. That just makes it really easy to find, even with just a small finder on your telescope. It's easy to spot it. So this is M13.
I want to point out something.
There is another feature that we like looking at when we have M13 in our telescopes. And if you look at the cursor, you can see that my arrow is kind of towards the top of the screen, top a little bit to the right. There's like a Y shape here. If you follow the pattern that I'm drawing with the cursor, and there's actually a dust cloud that's causing this, that's in the foreground of M13. It forms this Y pattern. And we kind of call it a Y or a propeller pattern. And when there's a good night of seeing, even with a small telescope, you can make that out.
Well, there was one other object that we are going to attempt. It's called the Eagle Nebula. If you've ever seen the Hubble Space Telescope image called the Pillars of Creation, that's a portion of the Eagle Nebula. The Eagle Nebula is a huge cloud of gas and dust where new stars are forming. We're going to attempt to image that, but it may not work out too well. In fact, the more I'm looking at it, the more I think that's not going to happen because we got the bright moon.
Yeah. I'm pretty skeptical on this one.
Yeah.
But let's try it. We got to lose, right?
We'll give it a shot.
Yeah, let's give it a shot. See what happens.
After that, the moon is now high enough to where we can point Nellie at it. So we'll do the Eagle first and then maybe finish off by looking at the moon. All right, I'm going to do another shift here. Find me a star to look at. To sync on. All right, here we go. So we're moving the telescope towards the south, and we're going to continue moving towards the south. But right now, all right, so I need to So we're synchronizing the software to the star field, so we stay pointing pretty close to where we want to be pointed. And now we're going to go down and find M16 here.
Yeah, you're looking at the previous photo we did still, which was M13. Well, Gerald points the scope.
What's wrong here? Oh, I can't spell M.
Oh, wrong key. You were looking for N13.
Yeah.
Or N.
All right, here we go. M16. All right, here we go. Too close to the moon. Yeah.
All right, I'm taking a 30-second shot at ISO 6400. That's pretty high, and it means it'll be a very noisy image, a lot of amplification, but might be able to make something out. We'll see what happens.
Yep. So the Eagle Nebula is a big, huge cloud of gas and dust, and it's slowly condensing to form new stars. But there are a few new stars that have already formed, and a couple of them are really big, massive stars that are putting out a tremendous amount of energy. Too much moonlight. Yeah. Yeah, you see it down on the left a little bit, but no. Yeah, I was afraid of that. We're too.
Let me try one last thing, and then we'll try a 1 minute shot of the solar.
So anyway, there are these massive stars. They're very young stars. Because they're so massive, they burn extremely hot, and they put out a lot of radiation. And radiation, light itself, actually has pressure. And that pressure is pushing the cloud of gas, causing it to be pushed away from all these lower mass stars that are still forming within it. And so what you see is like little fingers of gas extending up. And within those fingers, you'll see little, well, what we were arguing about the other day, whether we should call it a pimple or we should call it a nipple. But they look like little protuberances coming out of the fingers. And those are individual stars. And the gas that is condensing to form those stars is being blown away by those much more massive stars. So that's going to slow down the formation of those smaller stars, and they will not become massive stars. They will become stars more like our sun, low mass stars, possibly even lower the mass than our sun. All right.
You can see a little bit of it
Yeah, down
in the lower left
left
corner. Yeah, in this area right here, right?
Yep, that's it.
And that's really all I can see. And everything else is like either bloated stars or artifact. So I think it would require a lot of experimentation to get this right. So I'm not terribly impressed with the results here.
Okay,
Let me try.
so
Yeah.
so why don't we go to the moon?
That's a good idea.
So you're gonna have to take the ISO way down, maybe do
Yeah.
live
We can
view.
go and almost take a normal photograph here. I'm going to go to 400 and and probably take it, just start with maybe a
Well, how
30th
about-
of a second, or
How about live view?
yeah, we could probably do live view. We'll start with that, but I want to
Yeah.
I'd like to get some shots there. Go to live view. Okay. Yeah, go ahead and slew to the moon.
All right. Okay, here we go.
I think live view is terrible.
Yeah.
Hold on for a second. We'll stop with live view and just take regular shots here.
Maybe go to ASA 100.
Yeah. Got to go to 100. Let's go to. I forgot how big the aperture of this telescope is. That's, I don't know.
You know, we may not be on it.
Well, we are on something. I'm not sure what that is. We may not be on it. Looks like fire.
Let me check something with the finder. Hang on.
Yeah, I don't think this is the moon. Yeah, we found something completely new, which astronomers have missed for the entire human history.
Oh, God. Right.
Is it the moon?
It's in here, but it's off center. So let me.
I get it centered, and then I will get this down to.
You're not going to be able to see the whole disk.
No, okay. So that's what's going on here, right?
All right, give it a shot now.
Okay. I got to find the right exposure for this because I've never imaged the moon in this scope. It's funny, it's not really. Okay, there we go. That's looking more like it. Sorry, I had a set. It was stretching the image. That's why.
Oh.
So, you know, actually, it might be nice to try to find. Not exactly sure where we are on the moon. It sure would be nice to be able to look at.
It looks like we're a little out of.
Or.
Yeah, it
see
looks
if I
like
can
we're a
get a
little
live-
out of focus right now.
Yeah.
If you could go down to ASA 80 or something and
Well,
do
let's
live
try
view.
this. Let me try going to live view and change the ISO to 100. See if I can do that. It's not really won't let me do live view. Okay, so stop that, and we'll go back down to 200, 800th of a second. And we'll just do shoot. Okay, so maybe we should try slewing a little bit.
Okay.
And I'll just take repeated images here while you slew.
Okay, I'm going to go north. All right, try that one. I actually probably went too far.
Oh, that's actually pretty
Actually,
good.
that looks like, is that Copernicus and Kepler?
I think so.
Yeah, we're just not in focus.
Yeah, that's a little tricky. So let me see if I can improve that. No, I'm not going to be able to reach it. So we're going to have to live with it.
You can use the ladder.
Where is it?
on the other side. There it is. Bear with us here. We're a little out of focus. It's funny, we were really well focused on the stars, but bear with us for a few minutes here. Richard's got to work his way around a bunch of cables.
Wrong way. That's better.
Now, one of the problems with looking at the moon when it's a full moon is you have no shadows. So the crater that you see in the middle here,
I think that's
that's
about as good a focus as we're going to get.
okay. Is it possible for us to go either a longer exposure? Or,
Yeah, let me see if I can figure out a way to
I
brighten
mean, a
it up.
shorter exposure, get a little more contrast.
See what we can do.
Anyway, the crater that you see right in the middle with all the ejecta pattern around it, that's the crater Copernicus. And it's actually a moderately deep crater with a lot of cool features. But when the sun is directly on it, you have no shadows. So you get no sense at all of the depth of the crater or how high the crater rim is. So it's pretty disappointing. Most astronomers actually don't like looking at the moon or photographing the moon when it's full like this. Off to the left, you see another crater. That looks like Kepler. Let's see if we get anything better here. Yeah, so that's Kepler you see off to the left. To the right of Copernicus, up near the upper right edge, you see a curved mountain range. We name a lot of features on the moon after features on the Earth. And that curved mountain range is actually called the Apennines. So you're not muted, Richard.
Sorry about that.
There we go. So that's called the Apennines. It's named after the mountain range in Europe. And the Apennines, it's curved because it's actually the edge of a very large impact basin called Imbrium Basin. It's a huge basin. It's almost, it's about 700 or 800 miles across. And this was a big impact that happened very early in the moon's history, back about 3.5 million years ago. And the Imbrium impact caused the crust of the moon to be ruptured all the way down to what was then the molten core. The moon no longer has a molten core, but at that time it had a molten core. So you had all these cracks extending all the way down to the magma underneath. And over time, the magma rose up through the cracks and spilled out onto the floor of this big giant impact basin, filling it with lava. That lava is very dark in color, and it tends to be very smooth. So when you look at the moon through a telescope, you'll see these large dark areas, which are impact basins that have filled with lava, and the lava surface looks fairly smooth compared to the surrounding mountains, and much darker in color. So when you look at the moon with your naked eye and you can see dark areas and light areas on the moon, those dark areas are what we call the mare or seas, and they are impact basins that have filled with lava. So what do you think?
I think we get some pretty funny questions. That's what I think. Roman asked, can you guys point the telescope to the lunar rover left by the Apollo missions to finally dismiss the moon hoax? Well, I'll tell you, no matter, even with a big telescope like this, we still can't see the tracks left by the lunar rover or anything else left by people. Our resolution's pretty good. We can get down to what, like 50 miles or something like that. But the hoax was finally dismissed by some recent missions to the moon that actually photographed some of the Apollo landing sites and found the tracks left by the lunar rovers. Of course, people can say that those are fake as well, but we can't help
fake,
that, right?
Those are fake. The two moon rocks that we have here at Chabot, they're fake. It's all fake.
Let me see if we have any other questions.
I'm gonna slew north a little bit.
Yeah, go for it. And I'll take another shot when you've done that.
Maybe we can get up into the Imbrium Basin a little bit. Why don't you try it again, see what we get. No, didn't go very far, did I?
No, that did not go very far. We're in the same part of the moon there.
All right, try it now.
Oh, yeah.
Oh, there you go. Okay.
Yeah, the neat thing about scopes like this is it always looks like you're coming in for a landing.
Yeah. So you can see the limb of the moon off to the left. That big, smooth, dark area that you see basically from the center off to the right, that's Mare Imbrium. And it's kind of hard to see, but up near the top, you see kind of a half circle region that extends outward from Mare Imbrium. That's called Sinus Iridium. There's another feature to the left. I'm trying to remember the name of it. I want to say Aristarchus, but can't remember for sure. But anyway, it's an interesting feature because when you look there, in addition to impact craters, there are some volcanic craters there, and there's actually a channel. We can't see it in this image here, but if you look at Apollo images taken of that region, you can see a small caldera, volcanic caldera, and you can see the channel left by lava that had flowed out of that caldera. And now we think the moon interior is no longer molten, that there's no volcanic activity anymore on the moon. But every once in a while, astronomers will report what they think is some kind of smoke or bright flash from that region of the moon. And these are called transients. And unfortunately, they never seem to last long enough for somebody else to point their camera there and confirm it. So, but those reports have been consistent over the years. So there is a small possibility that there may be still a little residual heat under the moon's crust in that region. And once in a while, it puts out a little puff of smoke or maybe a little hot flash that shows up there. There's a lot of debate about whether it's real or not, but that's where people see it.
It could also be a reflection of water, ice, or something like that.
Right. Or some kind of rock that reflects light.
I mean,
under just the right
Chinese mission on the far side of the moon, they paused just this week at a location. There's a crater that had a strange green rock formation in it, and they decided it was molten glass. As at least that's one of the theories, is what they're looking at is molten, it wasn't molten glass, it was glass formed from molten rock at some point in the past, leaving behind just a weird green rock formation in the center of a crater. So maybe there's something like that going on in one of these craters that's reflecting the sunlight, catching it in just the right way. And it doesn't always happen. We had a few more questions. Is there a moon landing mission in 2024? And has there been a site that's been decided upon? This is not something I know about. So
Okay.
do you know anything about that?
Answer to the first question is we hope so. And the answer to the second question is no, we haven't picked a site yet. But yes, right now, the Artemis program, which is the Return to the Moon program, is planned to land on the moon, land people on the moon in 2024. That's a pretty optimistic goal. And when you talk to people in NASA, especially if you give them a few beers and get them away from the management, they may tell you that they're not so sure we're going to make it, but we'll get close.
I don't even think I can get my kitchen sink fixed by 2024. That is. I didn't even realize they were talking about a human mission. That seems very ambitious.
Yeah. So the plan is to send the Orion capsule, which has been in development for quite a while and is very close to completion. But they also want to put a spacecraft, a small space station, in orbit around the moon. It'll be called the Gateway. And the idea is that you fly not directly to the moon, but fly to the Gateway, park there, and then take a lander down from the Gateway down to the surface of the moon. So that's the plan. And the target date is the 24th or 2024. But they have not picked a site yet.
That's really interesting. I didn't know about any of that.
Yeah.
And
why don't we
sounds
take
really
another,
cool.
I've moved the telescope again, so why don't we take another
let
image?
me take another shot. Okay, let me do that. Nice thing is these get instant gratification here. I just take a shot. Oh yeah, look at that. Is that
Okay,
Tranquility?
no. Well, no. This is the eastern side of the Imbrium Basin.
Oh, it's Imbrium. Okay.
And you see the Apennine Mountains arcing up down from the bottom. You see Archimedes is one of the craters that's really hard to see. Right at the top of the image, you see part of a crater. It's actually a small basin. That's called Plato. And Plato is an impact that happened after the Imbrium impact, but it was filled by the lava that oozed up into the Imbrium Basin later on. That lava oozing up actually happened millions of years after the initial Imbrium impact. So the dark region that you see on the other side of the Apennine Mountains there, that's the Sea of Serenity. So that's the sea that's just north of the Sea of Tranquility. So maybe I can move it again, and maybe we can actually see the Sea of Tranquility here. I'm kind of having to guess a little bit on the motion of the telescope. Okay, why don't you take a shot now? Let's see what we get. Oh, okay. Well, we see the Sea of Serenity. That's the dark, sort of roundish open area in the left side of the image. The Sea of Tranquility. Yeah, you want to mute again there, Richard.
Oh, sorry.
Yeah. The Sea of Tranquility is right at the bottom of the image. It's the darker region that you see just at the bottom of the image. I'm going to move the telescope a little bit more and maybe we can get a better shot of that. But if you look to the right, you see yet a third dark region. That's the Sea of Chrysium. And if you look carefully, you see what looks like a bright crater with some streaks right at the edge of the Sea of Tranquility, with the streaks extending up into the Sea of Chrysium. Crisium, Mare Crisium. It's actually the Sea of Crises. Yeah, actually, I went too far now. Yeah. Okay, try it now. There we go. Perfect. Okay, Sea of Tranquility is right in the middle of this image. So the Sea of Tranquility has a little bit different type of lava than in the Sea of Serenity or in Mare Crisium. The Sea of Tranquility, the lava has a higher titanium content, and that gives it that darker appearance. In fact, if we were to really do a good exposure, not with this telescope, with a smaller telescope, to where we really got the colors coming out, you'd see that it actually has a slight bluish tinge, and that's because of the titanium that's in the lava that has filled the Sea of Tranquility. Now, the Apollo 11 landing site is down to the lower part of the Sea of Tranquility, a little higher, right about there. Yeah. And that's where it is. But no, we cannot see it with this telescope. No telescope on Earth can zoom in enough to see the landing site.
It's a good thing they painted a big bright arrow where they landed.
Yeah. Now, if you move your cursor up and to the right to that crater that I was talking about, that's Proclus. Keep going. That one right there, right there. Now, if you look at it, why don't you move your cursor out of the way now so we can talk about it. If you look at it, it's a round crater, but notice the ejecta pattern. It sort of sprays out to the left and to the right, and then a little bit of the ejecta sprays straight out in front of it. That's because the asteroid that hit the moon and produced that crater was at a shallow angle. And so when asteroids hit the moon and impact and produce a crater, the crater is round, but the pattern of the ejecta around the crater tells us what direction it was coming from and whether or not it was a shallow impact or a steep impact. Earlier, we were looking at Copernicus, and the ejecta pattern around it is pretty uniform in all directions. So that was a high angle impact, but this one is a very low angle impact. Okay, well, let's see. It's almost 11 o'clock here. So.
Yeah, we went longer than we usually do. A lot of people were asking, are we going to see planets tonight? Well, we're not, because there really aren't any that are in a position to look at tonight.
Well, hang on a
we
second.
might be able to get, you think we can get?
I think we might be able to get Jupiter. Hang on just a second.
We'll try. We'll see if we can get Jupiter. And if so, we'll see Jupiter and some of the Galilean moons if we're lucky. Careful, they don't trip. It's going to be really tough. Now, it's being blocked by the dome or by the tree?
By Rachel's dome.
Yeah. We've eclipsed Jupiter with our other equipment here. So, stay tuned as the weeks go by. We'll have more opportunity to look at planets and start looking at things that we normally don't see till late summer or fall. So we'll have our opportunity later on.
Yeah,
well, anyhow, we had a great turnout tonight. Huh? We had up to 190 people, and we got 130 people listening right now. I hope you had a good time. And,
any questions? You want to do some questions?
I haven't seen any others since the ones we just asked. Well, I'll wait another minute here. If anybody has any questions, go ahead and post them on Facebook. And I'll wait for a couple of minutes and see if any show up. Getting lots of thank yous. You're very welcome. This was fun to do. All right, you're welcome, everyone. Looks like we're just getting thank yous, and we're glad we could do this for you tonight. Have a nice weekend, and we'll see you next time.
All right, good night, everybody.